Uh, yeah, okay, now it's good.
All right, so I wanted to start out this morning by just giving an introduction to, thank you for joining us this morning, and I wanted to give an introduction to the IAEG AEG NOA Commission. So we're in an international group of NOA and EMP researchers, and we expanded from a group that got together after the 2018 IAEG Congress that was held in San Francisco. It was a joint IAEG-AEG meeting. Mark Bailey and I had been doing symposiums for a while in Oakland, California, and then we co-hosted a symposium in 2018 where we invited people from all over the world to participate. And after that meeting, we formed the International Commission of Geologists that includes Mark, Francisco, and myself. And we're an international team of geologists, industrial hygienists, chemists, and occupational asbestos experts. So when we were affiliated with just AEG, we had held 4 NOA symposiums in Oakland, and then we formed the Commission 39 for NOA in 2019. Some of our major accomplishments included that we published 20 papers in a special edition of the AEG GSA Environmental and Engineering Geoscience Journal, which was published in February 2020 and is available online today. And we issued a letter in support of the FDA Interagency Working Group. So this is the United States FDA, and for a while they had been waiting for the industry to kind of regulate itself. So for the past year, the FDA had an interagency group that had formed and included geologists, folks from the CDC in the United States, and they were researching and made some recommendations on asbestos and talc. And back to our commission, we have 4 sub-teams where we are working on guidance documents and methods, and those sub-teams include field methods, lab methods, mitigation methods, and area unite. So more on this FDA hearing on asbestos and talc. This working group has met for the past year, and they developed recommendations for lab counting and analysis. We think this is important because it's likely that if adopted, these recommendations may become definitions for our nationwide standard for asbestos analysis in talc in the United States, which would be an interesting development. It's very possible for this standard to become widely accepted for all NOA analysis. So important things to think about in here is that they pointed out that published methods that we have right now were not intended to determine the presence of asbestos in products at less than 1% concentration. So as we know, a lot of NOA particles in soil tend to be at concentrations at less than 1%, and a lot of our regulations are at less than 1%. Particularly in California, it's 0.25. They also recommended that TEM analysis method should be used for talc, even if the PLM results are negative. All the mineral particles should be counted, and then they think that the covered minerals that we should count and regulate should be chrysotile and all members of the amphibole group, not just the chrysotile and 5 amphiboles that were identified as regulated previously. They also recommended to count an aspect ratio of greater than 3:1 in the length of 0.5 microns. They also recommended that we adopt the term elongate mineral particle for any particle that has an aspect ratio of greater than 3:1. If you want to have more information on this, I left the website for FDA. This has the agenda for their hearing, the recommendations letter, and then also there's links to a video of all of the presentations that were done during the hearing. So let's get started on my talk. I'm going to talk about naturally occurring asbestos, specifically in California, where it occurs, regulations, mitigation methods, emerging issues. I'm Sarah Kalika. I'm a professional geologist in California, also a certified asbestos consultant, and I work for Diablo Geo Environmental Consulting. So in the United States, and I think around the world, there are 6 regulated types of asbestos minerals, chrysotile, which is found in serpentinites, of course, and then the 5 amphiboles. These were identified because they're the most common types that were mined for use in building materials. But it's important to remember that asbestos in rock is not necessarily considered a health hazard unless it's made friable. The threshold for regulation is generally 1%, like it is for building materials in the United States, except for in California. We have a lower limit of 0.25%. They were the most common types that were mined for use in building materials. So the threshold for regulation in the United States is generally 1%, like it is for asbestos in building materials, except in California, which has a lower limit. Though there are hundreds of non-regulated asbestiform type minerals that they're presumed to have similar health hazards by various research if they meet the 3-to-1 aspect ratio, meet the counting rules. Sometimes, depending on the lab used, they're reported. So in California, the Department of Toxic Substances Control, which regulates school development and school construction, and in some cases, other regulators, counties and air boards, they're increasingly interested in regulating the non-regulated minerals if it's listed on the lab report. At the Calaveras Dam project, which Bradley Erskine is going to talk about, he worked on that for 8-9 years. They identified dozens of non-regulated asbestiform minerals. So since about 2004, Brad Van Gosen from USGS has been mapping occurrences of naturally occurring asbestos in the United States. So on this map, and I know it's hard to see, I have two zoom ins in a minute. He has identified pink as former asbestos mines, yellow as former asbestos prospects, and then blue are other reported asbestos occurrences. So you can see that they generally are identified along the western coast of the United States and along the eastern coast of the United States. There's a zoom in on California. Obviously, that's probably why we have a lot of regulation, is because we have a lot of occurrences statewide. And then there's also along the eastern seaboard, along the Appalachian Mountain Range, various asbestos that used to be mined there as well. So where can naturally occurring asbestos be found? Lots of places. So rocks, outcrops, veins within rocks, fault zones, within soil and alluvial deposits. But it's always a good idea to not overlook the uphill, upgradient, upstream potential for sources because small particles can be found in soil miles away from a mapped unit. So if your geologic map says alluvium, look where that source is coming from. But then I've also heard on various construction sites that you can't, asbestos is not an issue unless we can identify it in the field, we can see it. Well, not necessarily. So just be aware that a lot of times individual fibers and then enough to count a rock or soil sample, at least in California, as 1% or 0.25% or even lower, you can't necessarily see the mineral fibers within the rock or soil sample. They're generally invisible to the eye, except for sometimes when they are. So if you joined us in 2018 in San Francisco, we visited this rock outcrop in San Francisco, and there were very clear veins of chrysotile. Last year in North Carolina, we went on a field trip as part of the AEG annual meeting, and we collected amphiboles right off the top of the gravel here, which was near a dunite mine. And then, of course, when you bring them back home, I like to put them in their protective enclosure. So the scale on this this fiber bundle here is about 2 inches. So we have a kind of a problem in the United States. There's no one comprehensive regulation, guidance document, training requirement, or standard of practice for naturally occurring asbestos. So the states have kind of cobbled their own resources together. And this is kind of a quick overview of the various regulations and guidance documents that do exist, but knowledge and understanding of all these regulations is based on an individual's level of effort to track down these regulations, to read through them, to understand them. And you can understand that it just depends on the experience level of the professional that you're working with. So what's required in California in my area? Well, it varies. It depends on what state you're in. So if you're in California, we're divided into local air districts. So it depends on what local air district you're part of. Sometimes it depends on where you are in the county. the amount of asbestos in your rock and soil sample, the airborne concentrations, if you're doing construction and trying to mitigate that, the size of your property and distance it is to a public area, and then the type of construction project. So a school and a hospital would be more regulated than a commercial area or a park, or even a residential area. So the regulatory limit of allowable asbestos in air, rock, and soil. So it depends on the type of project. If workers are going to be employed at your construction site, so if you're working on your own house, then you're less regulated than a commercial construction site. The size of the property makes a difference. So if your size is less than 1 acre, you'll have fewer restrictions than if your site is more than 1 acre. If people live or work nearby, so the threshold for that is about 1/4 mile. And then in some cases, it depends on if you've gone to a bank to get a loan to either purchase your property or to develop your property. Self-funded development, we found, can sometimes miss hazards entirely because they haven't gone through the bank and there's not any sort of requirement for an environmental background. Sometimes wealthy developers will just spend their own funds on things. Schools, if they're using state funding sources, require a more stringent oversight by the Department of Toxic Substances Control, but only on the portion of the school where construction is going to be occurring. So if a school already exists and they're going to expand, then they're under DTSC rules. But if they, the rest of the site doesn't have to be additionally screened. So we have various California regulatory limits. The first is essentially rock in soil, which is our airborne 0.25 by PLM. Though that's interpreted by various air districts, including the one that I work in, as greater than 0. So if you have any amount of asbestos, then your site is regulated as an asbestos project site. And DTSC, their level is 0.01%. So if the limit of detection for PLM is 0.25, so that's 1 fiber counted and a 400-point count, then that means that we must do some level of TEM to ensure their guidance level is not exceeded. And then also, if you're going to dispose of your soil at a landfill, it needs to be less than 1%, and also it needs to be not friable. And then the worker notification requirement for OSHA and the protection level is essentially any amount of asbestos. And there's also some asbestos content. So you need to protect workers if you're going to be, or if they're going to be exposed above 0.1 fiber per cubic centimeter sampled over 8-hour workday. Or Bay Area Air Quality has put together a 0.016 structures per cubic centimeter level, which is a guideline for protecting the public. So your rock and soil sampling analysis, it really matters. Obviously, you want to try to make sure that you're using the proper method. In California, we're required to use carb 435, though there are still people that don't understand there's a difference between carb 435 and asbestos bulk because both methods use PLM. Right, carb 435 is different. It requires specific crushing, sieving, and homogenizing, and not all labs do the same prep or mineral identification and counting. Breathing zone and air collection on a cartridge and pump is different, and there's a different type of cartridge and analysis method for perimeter monitoring or area air monitoring during a construction site than there is for personal exposure for OSHA. So I said California is divided into various air districts. There's a map of them. And all the air districts are the local enforcement authority to ensure that the air pollution is controlled within their jurisdiction. So therefore, each district essentially has their own policies and requirements for handling naturally occurring asbestos, with the general guidance that they need to enforce the air toxics control measures for asbestos. And there's also some written for other airborne pollutions. So there are 2 ATCMs that apply in California. One is for surfacing, so roads and things, and then the other one is for construction. And then each ATCM, it's written that they limit the use of materials that contain asbestos at greater than 0.25, as indicated by carb 435. So essentially, you can't have them remain on the surface to have vehicles travel over the top, and everything must be capped by at least less than 0.25% asbestos cover. So there are several air quality districts, not all of them, that require a written asbestos dust mitigation plan, and then air monitoring if your site is within kind of a developed area. An ADMP is required at all sites, but it's required to be reviewed by the certain air districts if your construction site is greater than 1 acre. So if you have a site that's less than 1 acre, then it's not required technically to be submitted to the air board, but you're supposed to still do dust mitigation. So the components of ADMP include construction site speed limits, limited to about 15 miles per hour, dust control measures to reduce visible dust emissions, roadway wet sweeping every 24 hours or as needed, methods to prevent essentially just dust generation during excavation, grading, loading, offhaul, anytime that you're handling the soil. There's also provision for making sure that you cover inactive stockpile. And if you're within a developed area, many air districts require air monitoring, though not all do. And so I recently found out that, the water misting techniques actually do matter. So sometimes, if you're out, you have a construction site guy and he's got a water hose, that may not be as effective to control the airborne dust. So essentially the theory is that if you have a larger dust particle, then you need a larger droplet of water. But if you have very fine dust particles, you need a finer droplet of water to pull that dust out of the air. So that being said, there's a lot of construction companies that don't understand this concept, and this costs too much to buy a special spray nozzle or to research it, so they just don't do it. So how do we know if dust control is working? We're required to do air sampling, a minimum of upwind, crosswind, and downwind of the construction site, and collect at least 8 hours to meet this carb-modified AHERA detection limit. So it's based on 3,000 liters of air at least. So if you're not able to monitor for 24 hours, about 8 hours is what it takes at 10 liters per minute to collect this much sample. Personal air samples by PCM are just not directly comparable. They're on a different cartridge and analyzed with a different method. And then how much airborne asbestos is too much? So in Bay Area air quality, we have an action level of 0.016 structures per cubic centimeter, which depending on the sample is about 20 structures detected in the sample. If this is exceeded, it's not that big of a deal, but the contractor just needs to put together a method and a procedure to keep the surface more sufficiently wet and to reduce the amount of dust. Though this action level is just not applicable outside Bay Area quality boundaries. So it's just for a certain small portion of California, San Francisco Bay Area. So also, if you have any employees on your job site or you are an employee, there's federal and state occupational safety and health administration worker protections for protecting employees from asbestos inhalation and exposure. In California, our local Cal OSHA agency has essentially declared that their interpretation is if you have greater than 1% asbestos and that the asbestos is in a material that is friable, then that's considered class 2 OSHA work requirements. So that means that respirators are required, protective clothing is required if you're going to be exposed above the PEL, training is required, you need to have a regulated area with signage, a decon area with waste water, you need to wear a respirator. Then if you're required to wear a respirator, the employer must have a respiratory written protection plan. I need to have a medical exam and fitness to wear a respirator, which is done through an occupational health doctor. Make sure that if you're going to be fit tested, you need to have a shaved beard or mustache. And the CDC has put together a handy chart, which is not specific to APRs. I think it was intended for like N95, which is not applicable for asbestos, but it's a pretty good at least example to show employees that like, hey, I have this kind of mustache and was that gonna be okay? Am I gonna pass my fit test? So you can tell them, hey, check out the chart. And that's it. Let me know if you have any questions, and you feel free to contact me either through the EMP Commission website, which is NOA-EMP.info, or through my email. Thank you.
Thank you, Sarah. I think we have time for one question, then we will move to the next speaker. If you want to speak, you have to unmute your microphone. Okay, I don't know if I'm not hearing Marcus. I see your lips moving, but I can't hear you.
Yeah, I open my microphone. I hope you can hear me now.
Yes, now it's good. Well, I have just a question for Sarah. Sarah, all the measurements that you do with TEM, are they yes or no response? Like when you detect asbestos, then you have a positive sample, or do you do any sort of quantification in terms of fiber per cubic meter or milligrams per asbestos per kilograms of samples?
Yes, so the results are generally given in weight percentage. So it's not just it's positive. We get the actual amount that is in the sample that was analyzed.
Okay. Yeah, thanks. Well, okay. I just
Francesco, is it? I typed a question in the chat box. I didn't realize you wanted us to speak. Is it possible to ask a question?
Yes, that was possible. Yes. Yeah, we must keep a little eye on the watch, but please go ahead.
Very quick question. Sarah, thanks for the presentation. Really interesting. Does California have guidelines on how they expect site investigations and drilling to be conducted in areas with NOA?
Yes, we have limited guidance documents that were prepared by the state of California. And some years ago, in 2001, there was a pretty good guidance document prepared by our California Geological Survey. And then also the Department of Toxic Substances Control, which controls school site development. They put together their own guidelines on on-site investigations. Though those are just guidelines. It's not a regulation that you perform an investigation a certain way. It's up to the geologist to determine how they're going to map the site and then where they're going to target their samples and how they're going to collect them.
Okay, so very well. Thank you, Sarah. And let's move to the next speaker, Dr. Mattenklott for IFA Germany. And he will speak about the German situation on identification and assessment of asbestos exposure. So please, Marcus, now you should share your screen with us.
Okay, I try again.
Yeah, wonderful. It's working already.
And I hope you can see the slides. Does it work?
Then write any.
Okay, fine. Yes, my name is Marcus.
On the email. And we
My name
just
is
reached
Marcus
90
Mattenklott. I'm a
participants.
mineralogist from Germany. Sorry?
That's okay. Sorry, Marcus. Go ahead.
Yeah, I'm a mineralogist in Germany, and I'm working in the Institute of Occupational Safety and Health from the German Social Accident Insurance. This is an insurance given by law, so to protect workers, to compensate them for any diseases, but also to protect the workers during their work. So everything I tell you now is concerning occupational safety and health, nothing concerning environmental or other items. It's just concerning occupational safety and health. So in Germany, we have a system, an established system working with exposures coming from natural occurring asbestos since about 20 years now. We established rules in the late 1990s. And I just can give you a brief impression on this system in total. So before I come to the analytical approach, I give you some impressions on the legal situation, the legal frame because this is need to understand in the end to interpret the results I present you from for asbestos contents of materials or for asbestos exposures. So I think we are one of the few countries that have a specific exemption for the handling of mineral raw materials potentially containing asbestos. In our hazardous substances ordinance, there is a sentence that says that the extraction, treatment, processing and reuse of naturally occurring mineral resources and mixtures and products made from them containing asbestos in excess of 0.1% by mass shall be prohibited. And this means that we are allowed to use these materials when the asbestos mass content doesn't exceed 0.1. And therefore, we have implemented regulations in the way of technical rules for hazardous substances. We have technical rules for any kind of chemical hazards, and this is the specific one, the TRGS 517, that is concerning activities involving mineral raw materials potentially containing asbestos and mixtures and products made from them. So you see the scope on the right side, and in these technical rules you find beside definitions, come to that, and information gathering. That means how to determine the exposure, how to determine the asbestos content, and also how technical and general protective measures have to be introduced. You find the set of protective measures for general work, and then branch related, you find supplementary protective measures. And what's interesting, there are annexes on one hand that tell you how to find out if you are working with a rock deposit containing asbestos, and two procedures how to describe the mass or to determine the mass content of asbestos in a material, and how to determine the exposure using these materials. The limit values we have in Germany are the one, it's a specific concept, it's a risk-related concept, not single limit value, but it's a tolerable level that may not be exceeded. It's 100,000 fibers, the same as on European level, on European Union. And there's the acceptable level, it's a lower level of 10,000 fibers. And generally, any kind of technical measure is done in a way that you should be below 10,000 fibers per cubic meter. The activities which are in the scope of this technical rule are printed here. I think it's the same than anywhere. It begins with extraction and processing in quarries, goes on for the whole building and construction field, for road and railway construction. It also includes the reprocessing and recycling of the material, especially when you have production of asphalt and have recycled asphalt material. It's the processing on work with natural stones. Very interesting also the cold milling of road pavings, the work in underground cavities, and a wide field of talc powders and other kinds of mineral fillers and additives for any kind of material like rubber, concrete, or repair or anything, or any other possible activity. So to understand how we define the asbestos fiber and the asbestos content in materials, we have an extended definition of asbestos. The typical definition doesn't tell you really how to determine the asbestos content in a material. So the first step, and the first one of the two important facts, is that decide if it's the fibers you detect on the WHO fibers you detect on a filter. It's not interesting if these fibers come from asbestiform or non-asbestiform source of this material. All the fibers are counted, and they are told to be asbestos if they are, according to their chemical composition, belong to the 6 asbestos minerals and show the WHO dimensions. And concerning the mass content of asbestos, it's interesting that the asbestos mass content does not necessarily correspond to the mass content of the asbestos mineral in this stone. Because we primarily look on the release of fibers of a material. So for us, it's interesting to make a relation between the content of releasable asbestos fibers and the material itself. So the mass content of asbestos is depending on the kind of mechanical treatment. And so it's also depending on the process and treatment of the material. It can change depending on the way that you use it. So to tell it in a short way, we typically go to their places where you have the highest dust exposure when a distinct material is used. For example, when you have crushed stones, you go to the crusher and take a dust sample and determine the asbestos content of the dust sample. This is the relevant asbestos mass content. It does not necessarily have something to do with the content of a specific mineral in the product. So in the early 1990s, we have some challenges in the analytics. The first one is that these crazy amphiboles, tremolate, actinolite, and even antipholite were not of interest in the years before. And we also had to look for very low asbestos concentrations, less than 0.1. And the next topic is my specific concern. Most of the laboratories didn't know that when analyzing mineral resources that you are facing also other particles from other minerals that look similar to asbestos. So you have to work on a distinction between asbestos minerals and other similar minerals in these raw materials. So we had three aims to fulfill when doing an analytical procedure. The first one is to include the mineralogical knowledge for the identification of asbestos on the one hand and the from other particles in these resources on the other hand. And this should be put into a convention that may easily be applied by different laboratories, not only high specialized laboratories, maybe on universities or so. And in the end, these conventions has to be so clear and so simple that the results produced by different laboratories should be comparable. Because in the end, depending on these results, legal measures oblige to factories, to producers, or anyone else. And it's fatal if two different results from different laboratories show you different levels of asbestos. So the first step to come near to this problem of identification is to see what typical appearance we have for these NOAs, and I think it's the same than anywhere. We have some ultramafic rocks in Germany, mafic, intrusive and extrusive rocks, and what's typically for Germany that a lot of these rocks are metamorphic or metasomatic alterated, typical schist, chloride schist, green schist, and something like that. And based on this scale of stones we have appearing here that are used in Germany, I try to reduce the amount of minerals that we look for to be similar to asbestos are reduced on 40 silicates. I show you some impressions on that on the next slides. So the first step is don't try to read all the data on these tables. The first step is you have to be clear about the composition of asbestos on other minerals. And please keep in mind, in Germany, we typically work with SEM-EDX analysis. So not only the ideal, but the typical chemical composition of the technical, but also NOA particles is in mind. And what is different to understand for a lot of laboratories, they have no specific composition, but you always have, or a lot of cases have solid solutions like by amphiboles, chlorides, or others. So we have a range of composition for a lot of minerals. And what's also interesting to see the technical data on ore-related chemical composition of different asbestos and looking for literature data for that. And besides looking only on asbestos, on the content of specific elements, you should identify relevant element ratios, significant like silicon, magnesium, silicon, aluminium, iron, magnesium, and so on. And the next step for this is to reduce the complex chemistry or what you can detect by any analytics to that what you can do by EDX. And to keep it simple and to make it comparable, you need a set of data for the evaluation that we try to do in a way that we normalized the whole chemical composition of 100% of the oxides of the elements printed here, natrium, magnesium, and so on, up to the iron sulfate. And at the end, you also have to do a little fitting because you know that these EDX analytics is not a real quantitative analysis, but only a semi-quantitative, because most of the laboratories in Germany don't work with standards, but standardless self-correction. So In the end, it works like in this example. You have the particle, you have a spectrum and a semi-quantitative result for these 10 elements, and you see they are these yellow spots in the picture on the right side. It's just a simple comparison, tremolit or augite, and you can see, depending on the element or content of calcium and iron, it cannot be augite, but it should be tremolite. So the red bars are the target value of the element for this mineral. And what happened when establishing these rules was that a lot of particles show a composition that neither come clear with asbestos or any other mineral. And so for that, you have to evolve a procedure that you widen the tolerance of the target values for the elements. You see this with these orange bars behind. So we do it in the procedure that we make an iterative extension of the tolerance range, 10%, 20%, 40%, up to we have a hit for this particle to show up if it's an asbestos or non-asbestos mineral. And this looks simple in a case when you only compare two minerals, but it gets very complicated when you want to compare the composition of a particle to see if it's one of the 6 asbestos or one of the 40 other minerals. And in this picture, you just see the main possibilities of deciding which mineral is it, just by element contents and element ratios. And what you see with the first blink is this cannot be used manually. It works very, very fine for a lot of distinctions, but you need an automatization for this. And so I constructed an Excel sheet. You see a screenshot of this. It's in German, but I explain you some of the details. This Excel sheet checks all the criteria by just putting the element contents inside the sheet. You see on the left side some yellow fields where you can put in the chemical composition found by IAEG, and it checks and gives you the best hit in relation to the asbestos minerals and other minerals. So on the right side, in the upper part, you see for the different asbestos types appearing as NOA particles, you see any criteria if it's fulfilled or not. And in the lower part, you see the 40 minerals for the distinction from asbestos, and the number behind them just indicates how many elements doesn't fit with the composition put into the left side. So this Excel sheet is available free as a download on our website, and we implemented this in the technical regulations. It's an obligation to use this distinction sheet when dealing with exposures or materials related to NOA particles. Any kind of natural mineral resources, and when you work with this, when you make measurements from occupational safety and health, you have to use this table. And this helps to bring comparable results in exposure data. How do we work on the determination of asbestos mass? So we have 4 different procedures described in the technical regulation. I show you 2 of them just in a brief way. So when you have, for example, a talc powder, you use the sample as it is. You just transfer an aliquot suspended on a gold-coated nuclear pore filter, and then the SEM-IDX analysis is done in an analog way as you do it for any kind of air sample. You just screen different fields and look for WHO particles. The determination of the mass of these asbestos particles is done by using the measured dimension of the found WHO asbestos particles and the specific weight. So you calculate by the found particles related to the aliquot you put on the filter, and so in the end you get a mass content of WHO asbestos fibers in the talc powder. The similar way is done for example, crushed rocks. You go into the quarry, and as I told you, you look for the dust produced by the highest dustiness points. For example, you take a dust sample, inhalable dust is the item in the crushing zone. And these dusts deal the same way as I told you for the talc powder, but the result is different. The result represents the asbestos content of the product dust. And if you want to refer it to the whole product, you have to divide it typically by the factor 100 because by a conservative estimation, the dust produced by such a mechanical process is typically less than 1%. So here at the end, some results for the typical asbestos contents of raw materials we use in Germany. The talc powders described here are typical European powders. So we had a random selection of 57 samples, and you can see that we found asbestos in about every fourth of these samples, and 13 samples in total. And when we found asbestos, the contents are typically less or around 0.1% mass percent of asbestos. And what we typically also develop, it's an obligation that we determine the number of fibers per milligram. It's a very important information doing this because when you make a qualified analysis of any powder, you have a very interesting information and a relative information about the potential of release of asbestos from a material. You see there's a big difference here. It divides between 800 and 50,000 fibers per milligram. Typically used materials, crushed stones are serpentinite, only a few, but most of it is gabbro, diabice, or amphibolites, and some other metamorphic rocks. And you see that the serpentinite is the most critical material, which shows about 0.7 up to 0.7% of asbestos in the analyzed dust. And the typically used material for construction sites, roads, and anything else shows contents up to 0.1, 0.2%. The limit of detection is an estimated one. We estimated it up to 0.008 because the basis for the analytics is the Poisson statistics, and it says how many particles you won't see when you analyze a sample. Because you can't determine the dimension of the particles you won't see, you only can estimate the LOD. So this is something that looks crazy because you sometimes have lower contents determined than the LOD tells you. At the end, some data from the exposure workplaces. We have data from quarries, production of asphalt, cold milling of road pavings, and talc powder, use of talc powder, manual powdering. And you can see that for most of these applications on the operations, the 50% value of asbestos fiber concentration is in the range of 10 to 20 or 30,000 fibers per cubic meter, if you have asbestos in them. And the 90% value shows the critical parts. And this is, for example, the processing of materials in quarries. You have the highest exposures. And that means that you have exposures up to 230,000 fibers. The same for production of asphalt. You can see that the high dustiness processes give you exposures up to 70 or 84, 85,000 fibers per cubic meter. Some operation that may also be critical is the cold milling of road pavings. Typically two persons are working on this, the machine operator and the man aside, and we have a 90% value of exposure of about 7,000 fibers. What's interesting is the use of talc powder. I told you about a quarter of the samples we analyzed showed asbestos in them in very low concentrations. And now we have a data set of about 68 measured values for exposure during manual powdering, and we only find in less than 10% of these samples asbestos fiber concentrations in the range of about 10,000 fibers. So I will finish with that, and thank you for your attention.
Thank you very much, Marcus. Thank you. It was very, very interesting. I'm pretty sure there are several questions for you, but I asked the audience to keep the question for the end of the session because we are a little late. We want everybody to be able to speak.
No problem.
Okay, yeah. Thank you, Marcus. So, Bradley, are you there? Wonderful. So,
and I'm okay.
Dr. Erskine from Erskine Environmental Consulting, USA. He will talk about the Calaveras Dam replacement project in California that was previously introduced by Sarah. So, Bradley.
Hang on, I'm having a little trouble here. Let's see.
That's okay. We can see your mouse. The mouse is moving somewhere, but on a gray screen.
Oh boy, I'm having trouble getting onto my PowerPoint here.
Yeah, just try to share the screen again.
I did, but now I'm having trouble getting. Oh boy, sorry about this. Okay, am I there? I'm having some trouble here, some technical problem.
Right. You know what? Maybe we can move to RL if
Yeah,
she's
I'm having technical problems here.
available, and try to fix. Maybe Sarah, can you try to give a hand to Brad, and RL? Would you try to share your screen? And yeah, thank you, RL. Sorry, Brad.
It's fine. Go ahead. I'm gonna leave and come back.
Yeah, wonderful. Thank you.
So can you see my presentation?
Yes.
Okay, great. Okay, thank you. Thank you, Francesco. So I am glad to be here in front of you to present you a project called Carto PMI in French. It can be translated in English by EMPI Mapping Project. It is coordinated by OPP-BTP. So I'm the operation manager of the project. Christine Denevillers is the leader of the project, and Patrick Richard is the technical director of this project. So first, I wanted to present you briefly the institution, and then I will present you the general aspect of the project, the settings, the goals, a detailed definition of EMPI and the type of measurements, and the two main phases of the protocol, that is protocol tests that are set up during the exploratory campaign. And then I will conclude. OPP-BTP is a French construction industry body for occupational health and safety. It was set up in 1947 by the social partners of the French construction industry, so by the worker unions and both unions. So we propose a full range of services: engineering, consulting, and advisory, training, information, and documentation on any kind of risk in the domain of building and public works. We are at the service of construction companies, professional bodies of the construction industry, and public authorities. So the technical direction that is leading different kind of projects, as asbestos mapping, crystalline silica mapping, is based in Paris. And on the map of France, you can see the offices in the different region of France. So, sorry, it's not moving. First, issue of cleavage fragments started in France in 2014 by the during the identification of this kind of fibers in aggregates of manufactured materials, mainly bituminous pavement. And we could see some discrepancies between laboratories results, and we are mainly faced by actinolite kind of fibers. Most of the time that was not asbestos, but that was identified by the laboratories as asbestos. So the government asked the ANSES, that is the French Agency for Occupational Health and Safety, to make a study on the health risk related to cleavage fragment fibers. The results were published in the first report in 2015. And after that, the government asked again the agency to work on analytical methods allowing distinction of these fibers, to make a study of the aggregates economic sector to identify EMPI sources. So these results were published in the second report in 2017. So the ANSES defines the concept elongate mineral particles of interest as EMP of 11 mineral species of respirable fibers that are a ratio of 3:1 over 3:1 and a width under 3 micrometers. So based on this recommendation of ANSES, the French government asked the OPP-BTP to coordinate a project on the population exposition to the EMPI. This project is called CARTO-PMI. The partners of the project, we have a pilot committee that is composed of the coordinators, so the OPP-BTP, and of 3 ministries. The Ministry of the Work, the Ministry of the Environment, and the Ministry of the Health, of 5 directions. The technical committee is composed of the technical agents of the ministries and of the 6 main scientific French organisms that are ANSES, INRS, that is equivalent to NIOSH, the Geological French Survey, that is the BRGM, INERIS, CSTB, and CEREMA, and some independent experts are also involved in the project. The main goal of the project is to give reliable data to the 3 ministries in the aim to legislate proportionally to the EMPI exposition risk of the workers and of the public population. So as I said, the project is based on the recommendation of the second report of the ANSES, entitled Identification of Emission Sources and Propositions of Protocols for Characterization and Measurements. So CARTO-PMI refers to a process of project management developed by OPP-BTP, and it is based, among others, on supervision of measurements on the field and single measurement protocols. So here I present you more in detail the definition of EMP according to ANSES. So the elongate mineral particles are the mineral particles with an aspect ratio of length and width over 3:1, whether they are asbestiform or non-asbestiform particles. So you can see, you get used to see this kind of photo of asbestiform fibers on the left and non-asbestiform or cleavage fragment fibers to the right. So in this project, In the air, the measured particles are the respirable EMP with a width under 3 micrometers. So, what is EMPI? They are the EMP of interest. So they are the EMP of only 11 mineral species. They are the 5 amphibole of the asbestos minerals that are actinolite, tremolite, and sulfurite, grinerite, and rebecite. They are serpentine, so chrysotyl and antigrite, and they are the 4 other mineral species that are considered cancerogen for humans. So they are vinchite, fluoroedenite, richterite, and erionite. So in France, asbestos refers to the 6 fibrous silicates, and they could be intentionally added or naturally occurring asbestos. And the cleavage fragments refers to the forms of the 6 mineral species, and they are non-asbestos. So the ANSES, so this agency recommends to apply the precaution principles to the EMPI with these 3 dimensions that are a ratio over 3, a width under 3 micrometers, and a length over 5 micrometers, carrying the whole work health and environment regulation related to asbestos. So it could have a really big social and economic impact. For this project, we do 3 different kinds of measurements that are explained in 2 different protocols. The first protocol deals with the bacterial characterization. So it explains how to do the sampling of rocks and aggregates, and it has to be done by the biogeologist. And it also explains how to do the procedure by PLM for the rocks and also completed by TM. The other measurement concerns the air sampling and to evaluate the worker population exposition. So we do 2 different kinds of sampling on the workers with a mobile pump. The analytical method is the TEM, and we do also workplaces sampling by static pump, and we do also an analysis by TEM. And for the public population exposition evaluation, we put a static pump at the limits of the construction sites and of the quarry, and we use also them for analysis. So the main steps of the project are first test. So during more than 1 year, we worked with the COTEC to prepare to test the protocols on the site. So we tested the 2 protocols on a quarry. So we had to prepare the measurement with the professional organization and with a private company to do the test and to modify the previous protocols to get finalized protocols that are set up for the exploratory campaign. So these protocols have been validated in December 2019. So we started to prepare the exploratory campaign. We should have started the measurement in April, but because of the crisis, we have to delay the measurement. But we worked with project sponsor to establish which kind of situation are the more reliable for the goal. And so now we are working with a professional organization to prepare the campaign with the private company to finally do the measurement. The test protocols were quite a huge staff. We have two protocols, as I said. The first one entitled Exploratory Measurements of Mineral Species in Materials Susceptible to Liberate EMPI. And the second protocol is Exploratory Measures of EMPI in the Air. So the implementation of the protocols was done to make them strong and also homogeneous. So we did in situ tests and interlaboratory comparison to be sure that the protocol was ready and was could be reproducible. And we did more than 15 meetings of the COTEC to adjust and modify the protocol. And also we developed a specific chemical data treatment based on the Leocat file. So these protocols are very complex and experimental. We need more than at least 6 weeks from the sampling strategy to the analytical report. And these protocols are specific for projects. So the exploratory campaign, 2 different will be tested. We will make the measurement in natural environment during earthworks, and we will do the measurement in quarry that project aggregates. The studied works are the most susceptible to contain mineral species of interest, so they are amphibolite, dolerite, metabasalt, metagabbro, and we study the product action pairs to evaluate the EMPI exposition, for example, rocks and breakers, aggregates, and grinding. So now I will conclude. So take-home messages are that is a very big project. We have 3 ministries and 5 directions involved in the project. This project is upstream to the health, work, and environment regulation. We have 2 measurement protocols that have been tested in the field, and that is exploratory measurements and data acquisition project. And the impact on economical sectors is very wide, and it needs high scientific level as all the scientific French organisms are involved in the project. And I could see that some people in the project are in the public now. So there is Cédric Duet from the Geological Survey and Marianne Shane from the CEREMA. And so we are waiting for the results of the measurement, not in 2020, but in 2021 because of the delay due to the COVID. So thank you. Thank you for your attention.
Yeah, we should add some clapping hands at the end, sound at the end of the. Sorry.
Thank you,
about
for
the silence, but everybody appreciate your talk. Yeah, exactly.
Okay, so, thank you.
Well, we have.
Hello, everybody. Thanks for joining the symposium. Thanks to all the other speakers. It's really exciting to hear about the work from other countries and other agencies. And I think you'll see through this research that all of our work seems to be reasonably complementary. And so I'm really looking forward to potentially collaborating with the work in these other countries. Okay, so today, sorry about that. Today I will be looking at the EMP research at NIOSH and essentially actualizing the asbestos EMP roadmap. I do, I'm the project lead, but essentially the work is done by our research team, and this is the research team at NIOSH. So most of the work that I'll be talking about today, which will just be summarizing several of the research tasks that we've been looking at, are done by the team here, and their emails are available if you have any questions. So just to start off with, I'd like to just put the definitions out there of what I'm talking about today. And everybody sort of knows this, and this goes along with a lot of what the previous speakers have discussed, saying or showing that there's still a lot of confusion about terminology and about measurements and such. So today in my presentation, when I talk about asbestos, I'll be talking about the commercial term of asbestos, which is only one group of a larger class of elongate mineral particles. And for this research, NIOSH is going to use the broadest definition of EMP, which is similar to what we've already seen in the previous few speakers, but really comprising all particles, meaning any definition of EMP, including length and width and aspect ratio. Several years ago, NIOSH published the Asbestos Fiber and Other Elongate Mineral Particles State of Science and Roadmap for Research. That's the title of the document, or the cover of the document. And it laid out a certain pathway for research in certain of the areas that needed to be looked at. Essentially, it looked at us to develop a broader and clearer understanding of the important determinants of toxicity for EMPs. It wanted us to develop information on occupational exposures to various EMPs and the health risks associated with those. And it wanted us to develop improved sampling and analytical methods for asbestos fibers. Our own National Academy of Science reviewed this and gave us some additional comments on that, which we were then able to incorporate and hopefully, again, further incorporate into our research. So essentially the strategy that the NIOSH created was, or we were hoping to create as an agency, was first of all to create a centralized home for EMP research within the government. And this is within our own research area. So we created a minerals team, we created a laboratory in Pittsburgh, and then we're hoping to put together a larger coordinating group with other agencies within the United States government and other divisions within our government to help us with this research. We'd also like to establish relationship with research partners. And these are agencies outside of NIOSH, so sister federal agencies. We're working with the USGS and EPA and FDA, other academic organizations, and analytical laboratories. So we're still in the process of creating these relationships. The project is really just finished its first year, and it's a 5-year project initially. We're expecting it to be a much longer project. So we're still starting to develop these research partners. And then finally, we're going to develop this EMP program. And again, that's sort of just looking at specific tasks and specific aims that I'll be going through next. So for this particular project, we have 3 specific aims. We, as an organization, the Pittsburgh Mining Research Division, we work with underground miners. So our specific mission is to try to understand the potential exposure to miners to asbestos and other elongate mineral particles. And we'll be doing this by analyzing, bulk material or samples that we've taken from mines across the country. And this analysis will really be driven by geological knowledge of the deposits and their host rocks. And the idea here would be to give our mining stakeholders the ability to understand potential hazards if they're working in a certain type of commodity. Our specific aim 2 is to further elucidate the toxicology of these elongate mineral particles And we're going to do that essentially starting by trying to separate EMPs by different characteristics. Of course, the one we're going to start with first is length. So we'd like to start doing toxicity experiments using particles of different lengths. So if we could create different size ranges, for instance, a size range that has particles only less than 5 microns versus a size range that has particles only greater than 5 microns. We think that, and we can run toxicity experiments on these, we think that would really help to elucidate this toxicology and at least give a firm grip or a slight grip on what characteristics or what are characteristics of concerns. So we're starting with length. We would like to incorporate other characteristics as we are able. In the third specific aim, and I'm going to go through each of these specific aims in more detail as I go along. The third specific aim is really to investigate applications for analysis and for measurement of EMPs. So in the mining area, we've done a lot of sampling that we do time-weighted average sampling, but we're sort of moving to doing real-time analysis and real-time sampling. And so we would like to be able to establish a technique for EMPs. And I know everybody on this seminar right now is wondering how that would be possible. And we're still wondering that as well, since the current techniques to measure the exposure to EMPs are reasonably detailed and complicated. And so we will be looking for, throughout this research project, for ways to develop this. We haven't really started working on the specific aim 3 yet. So although I have a slide on it later, there'll really be more to come there. Okay. I'm having a problem advancing my slides. There we go. Okay, so task 1 of specific aim 1 is to understand the miner's potential exposure to asbestos, as I had already discussed. And what we would like to create under the task is using the detailed characterizations of these previously collected samples. We'd really like to create a database of mine geologies. And we're starting, this will be in the United States, with the idea behind a mining company or stakeholder would be able to use our database, and they could look at areas that they're interested in mining, and then decide whether there's a potential for having exposure to EMPs. And then they'd be able to incorporate that into their health and safety plans. So we're hoping it could be just used as a tool to ensure ensure safety and health on the in the future mine that they would be creating. But the nice thing about this for the stakeholders is they'd be able to have this information up front, so that they'll be able to understand the potential anyway, and then they can use current information to create good health and safety plans. This is sort of an example, or just a Google Earth picture of the mines that we've collected samples from over the years. Most of this information is coming from a database that NIOSH collected a long time ago. But you can see we have a fairly good coverage of the United States. And on the left, it sort of shows the facilities by commodity. So we have a large number of different types of commodities that we think will be, once we characterize them, will be able to give us at least an idea of what potential exposures to miners working in these types of commodities may be exposed to. The other task would be just to develop standard classification for EMPs encountered in the mining environment using geology and mineralogy and physical characteristics. And again, we've already heard this discussed today, that the terminology still is slightly confusing. There's a lot of imprecise terminology being used. Everybody uses different definitions, and so we're hoping through this project that we'll be able to at least refine and have people agree on the terminology that can be used. And most of this will, of course, be based on the detailed characteristics of these EMPs. And then potentially we could create a unified classification system. And I know that each of the previous speakers had already discussed this, that this would really be a great, or would allow us at least the ability to have a unified way of discussing exposures and to discussing our work. And I realize this is a goal that may be far in the future, but again, I think most people would agree that this would be useful in the larger scheme of things. So task 3 is something that we're actively working on, is evaluating the effect of milling and crystallinity on EMPs. And again, some of the previous speakers have talked about the need to process bulk material in order to do some of these measurements. And some of the past literature has shown that when you process these EMPs or these bulk materials, you can actually change the characteristics of the minerals depending on what type of processing techniques you use. So when we were before we wanted to start using or move into the toxicity of these experiments, we thought it was very necessary to understand if the milling or the processing of these bulk materials could have an effect on that toxicity. So we're going to go through 5 or 6 processing techniques, and then once we process the material, we will use that to collect the respirable fraction of that material. We will characterize that respirable fraction, and then we'll also do some toxicity work. And we would do this based on processed and unprocessed samples of this material. And by doing this, we hope to be able to discover whether these certain types of processing will affect the toxicity or the characterization. And then we could come up with maybe a standardized form of processing that can be used in the future. Once we have figured out the processing, then our idea would be, again, to separate the materials so that we could decide what important toxicity characteristics of these EMPs. And we've been looking at several different ways of doing this. Ultimately, the problem would be to first find a way to equally separate these into very separate size ranges. And then second is to be able to use that separation technique to collect enough material to be able to do toxicity. And those two are not easily equated. Because oftentimes, if you have a good way of separating, you may not get as much material out of that separation. So we've tried several techniques. We've used the aerodynamic aerosol classifier shown here, which actually does a very nice job of separating the material, and we can get very defined separation, as we can see here. However, the amount of material that you collect is reasonably low, so we would have to run this sample for a long time in order to collect enough material for toxicity experiments. Next classification we tried to use was a multi-cyclone sampling array. This was an array that could give us plenty of material. However, we found, as you can see here, that the separation wasn't so great. So the separation between the smaller size bins and the larger size bins that we were able to do, wasn't large enough. And so we didn't, and the point here is that if we say we have a less than 5 micron size range, but we also include a bunch of particles that are larger than 5 microns in there, then we're not doing proper toxicity experiments, because the toxicity could be affected either by the smaller particles or the larger particles still in any of those not well separated material. So this multi-cyclone array wasn't able to separate things properly. We came up with this third technique of separation essentially by filtration. This seems to, at the point, solve both problems. We're able to get very good separation, shown in the graph on the left, but also we're able to get enough material where we can actually run these toxicity experiments. So we're excited about this. We actually have started now using this to collect 2 different size ranges, and then we will send those to our laboratory in Morgantown to do the work. Of course, all of this work I've been talking about has been interrupted by the COVID pandemic. And this is an example some pictures of the separation. The one interesting thing you can see on the right-hand side is when we separated the non-asbestiform into longer particles and smaller particles, you can definitely see a difference in the shape of those particles, and oftentimes these will be counted as 3 to 1. But I think this would all be reflected, hopefully, in the toxicity. The idea is that we'll be able to get a standard aspect ratio for between these two samples, and so we're still working on that. Also, we've been looking at a way to sort of semi-automate the particle measurements. What we do with everything is we collect them on a filter. To do a size distribution, we collect the separated materials on a filter, then we look at that filter, and we essentially have to physically do the size, count and size each particle by hand from an SEM. And what we're trying to do is figure out a way to automate that sample, just to be able to move these samples through analysis quickly, and also have a much more standardized sampling technique that wouldn't be affected by an operator, the person who's actually running the sample. So we've been doing this type of work, and this is hopefully something we'll be able to report on in the future. Some other work we're doing, and I know RJ Lee has done a little bit of this work as well, and we've worked with Brian Bandley a bit, or talked to him at least, looking at EBSD and using SEM. So this is something we thought maybe when we're looking at techniques that are a little slightly less complicated or maybe easier to use, that this may become in handy. Again, we're at the very early stages of trying to of doing this work. And finally, for my last slide, this is for the specific aim 3, is to investigate sort of an end-of-shift way to measure EMPs. And I think there are some interesting ways to do it. We've seen some FTIR work that may actually show that there are elongate mineral particles on a filter sample. But again, we're very early in this work, and we really we'll hopefully be reporting on this in the next few years. So that is my short summary of the current NIOSH EMP work, and I'd be happy to take any questions if we have time.
Thank you, Stephen. Thank you, everybody. Now with Stephen, we are finishing the first part of this meeting. Now we have 2 flash communication from Alessandro Gualtieri, that is actually substituted by one of his colleagues from the lab, and from Selmaoui from University of New Caledonia. So I would just have Dario do the talking, and then we go to Naza, and then we will have time for questions. Sorry, Stephen, we can postpone the question for in a second.
Sounds good.
Dario, do you want to share your screen now? Yes. Speaker is coming from New Caledonia. It's 4 in the morning now in New Caledonia. She's winning the prize for the toughest speaker. So I hope that that counts somehow. And thank you, Christine, for joining us at this time. So I don't hear you. Is your microphone on? And I don't see you. So we can see your screen, but not. We don't hear you. Yes, now some. Okay, very well. Yeah, your webcam is behind the monitor.
Yeah.
Okay, very well. The screen is great. So.
I'm sorry.
Are you sharing your screen? Not just the application. Just please share the whole screen.
Yes, that's it.
Yes, wonderful. Yeah, yeah, that's great. Okay, thank you, Christine. And
So thank you, Francesco, and thank you to all for the high quality of all the presentation. So good morning or good evening, I don't know really. My talk concerns the exploitation of the potential of the machine learning for the identification and counting of asbestos fibers. This is a French-Italian work. Okay. Nothing change.
let's try to.
Assessing the risk associated with the presence of naturally occurring asbestos outcrops requires monitoring the quantities of asbestos fibers released in the environment. In New Caledonia, the nickel mines, which concentrated 25% of the world's resources, have in NOA. The protection of workers requires an increase in airborne sampling. However, the standardized procedures for identifying and counting fibers are long, complex, and depend on the choice of experts. This can lead to a bias between several experts, for example. It therefore seemed appropriate to develop an automatic procedure for detection and counting for fibers from images. The images we used to support our work come from simple photographs of filters from laboratory experiments. They are photographs by optical microscopy. The counterpart of a very simple photo shoot is that they have effects. For example, a non-uniform lighting and the presence shadows. The objective is therefore to obtain from the raw images the fibrous concentration and morphological parameters of each of them. This slide greatly simplifies the method followed. The raw image undergoes pre-treatment to eliminate heterogeneous background and increase the contrast of the particles and fibers. A thresholding and morphological transformation allows to eliminate the shapes coming from the which are not particles or fibers. The identification of the fibers initially requires the creation of a learning base constituted from the expert's recognition of fibers on numerous filters. A statistical sorting is then possible on all morphological pillars. This database feeds the automatic learning process by machine learning for the recognitions of fibers on new samples. One of the major difficulties is the presence of juxtaposition of fibers and particles. The determination of the skeletons by weighted thinning allows the individualization of each fiber. The final result is a compilation of all morphological criteria for each fibers. Each identified fibers is indexed. It's therefore possible to link other parameters to each recognized fibers, such as their chemical composition. So, from simple images of raw filters, our method allows a satisfactory detection and counting of fibers. It's a fast and inexpensive method that allows the multiplication of analyses in the direction of an improvement in the prevention of sanitary risk. We hope to produce a complete automatic monitoring tool that reduces analysis by being statistically robust. Currently, a program compatible with IAEG is under development. Thank you. I said 5 minutes. I did 5 minutes.
Thank you so much, Christine. You were perfect. Exactly. Everybody can clap their hands now. So okay. Now it's we are still quite a large number of people in the room. So I'm very glad everybody had the opportunity to speak without any excessive inconvenience. So the audio and the video was really fine. And I think we have time for talking, but now it's the point when the Americans and the European divide, because we can have our beer because it's almost dinner time, and the Americans should keep I think the coffee on the desk. So just
you don't know how we roll over here.
Very well. So I hope that you wrote your questions somewhere because if you want now, we have time to open the audience to question. So possibly we can ask a question to Christine first, since it's 4 in the morning and I think she deserves some sleep, and then we move to the other speaker. So is there anyone that want to have some details on the machine learning algorithm they are trying to exploit to recognize asbestos fibers?
Yes, Markus here.
Yes.
I have a question. We also deal with this item a long time ago. We did this in practice for optical microscopy and then started doing this with algorithms for pictures from nuclear pore filters. There were a lot of problems with this nuclear pores itself, imitating something like elongated particles, and there are a lot of mathematical algorithms for that. Concerning the optical microscopy, my question is, the problem with the optical microscopy is that the particles are not on one surface, but they are partly deeper in the filter material than other particles. So when looking for elongated particles, are you looking for something like a stack of pictures to reconstruct the fibers through with the whole length? Otherwise, you will only see a part of the fiber, and the rest is not in focus. So there are something like focus stacking softwares that reconstruct pictures from different levels, from different focus levels.
Mm-hmm. That's true. Christine, do you have an idea on how you can solve this issue, or you have it solved it in the past?
I'm not the most relevant for the real computer science aspect, but what I know is that in the algorithm we use, partly in the skeleton algorithm, we reconstruct, we rebuild the fiber shape. But you're right, we can manage this issue with the 2 dimension of the image and not 3 dimension. So you're right.
Okay, thank you.
Oh, yeah. You're welcome.
Yes, of course, things are easier with using SEM picture, and but when you're using optical microscopy, it's a big issue. The several focus plane you have to take care of.
Yes, but you have other problems using SEM pictures. You have more relict in the pictures. It's much more difficult, I think, to identify fibers on the SEM picture. For example, on the filter, on the gold-coated filter with all the effects of loading and so on, than on an optical filter, or the filter of your optical microscopy.
Okay, we have been using only SEM in at the University of Torino, but now we will see with this new algorithm. Apparently, SEM is working not that bad. We published a paper on Talanta 2 years ago. Maybe I can share that with you, Marcus. And
yes, would be interesting. And in Germany, we have a project. It's from colleagues from the Bauer, it's a statutory institution in Berlin. And they try to reconstruct fibers digitally by looking on SEM pictures of nanotubes. So this is the high end, I think, because nanotubes have a much more complex morphology than simple asbestos fibers. They have different curvings and so on, and we hope that as one of the results of this project, we might also get automated counting of asbestos fibers. We are together with them. My part is the identification and differentiation of different types of fibers. On the other hand, the counting of fibers. So that's also in Germany a very interesting project.
Okay. And I see there's also on the chat an intervention from Frank Ehrenfeld from ISTM that is talking about the 2021 summer conference about the use of artificial intelligence to recognize the particles. So Frank, say something about that.
Yeah, I'll chime. Some of the work from a company which I recall is based out of Paris and London, X-Rapid, X-Fiber, I can't remember the exact name. They had been working with artificial intelligence and looking at elongated particles on filters. In the last 2 years, they've actually made some significant headway, so much so that a number of studies were conducted to verify and validate. And we were one of the labs that was part of that study. And all the data was going to be presented this coming July. That will now be delayed as the entire conference in Vermont will be pushed to the summer of 2021. But I will offline separately communicate with the last presenter and try to compare some notes so that there can be some harmonization as to what's going on. I think it's probably the wave of the future, and the more we can refine that process and understand it, the better.
Okay, very well. So,
yes, yeah, thank you.
Christine Laporte, she will be glad to hear from you.
Yes, absolutely.
Well, just to remind you, everybody, so the recording of this conference will be available on the IAEG Commission website, and we will tomorrow we will collect email addresses of people that want to be connected. If you are not able to join tomorrow, just send me an email and we will put you in our mailing list. And so there will be a way to keep in touch. Is there any other question for Christine? Okay, fine. Then maybe the other speakers. Yeah. But why don't you stay a little longer, Christine, with us?
I need to wake up my children in half an hour because it's the beginning of the day.
Very Well, thank you so much. It has been great.
See you tomorrow.
Yes, exactly.
Bye-bye. Thank you all.
Bye-bye.
Ciao ciao. Ciao Francesco. Elena.
Ciao, Elena. Hello.
Bye bye.
Okay, you're leaving the room. Okay, bye-bye. Not waiting for the beer. Okay. Marcus, I have a question on.
Parlavo con gli altri.
Yeah, so I think it's time that we take the beer out of the fridge, right? And yeah, I think I was preparing to doing this.
Oh.
Look at that. Yeah. Okay, that's beer from Sardinia.
You call that beer? You can see through it.
Come on.
So I'm in my office. I would like a beer, but I'm not allowed to. And if this goes over internet, I have problems.
Okay, I see. Marcus.
Hey, Francisco, I have a question for Marcus, if I could.
Yes, please go ahead.
Hey, Marcus, on your presentation, something caught my eye. You had a diabase unit, and you showed from none detect to is a little over 0.2% asbestos in that. And what first question is, what was the amphibole or what was the asbestos species of that? And secondly, is that from the primary magma of the diabase? Was the diabase metamorphosed? So you might have had a replacement of, like, say, hornblende, ectanolite, or something to that nature, or were there veining? Where did that come from, that asbestos?
So the most asbestos we find in mineral resources is tremolite and actinolite. Only small portions of antophyllite, and really rare is chrysotile. Sometimes there are veins. For example, we have a gabbro quarry, and we have some veins of chrysotile. But most of the mafic stones in Germany are alterated and metasomatic alterated, very low grade, low to medium grade, and this means typically we find something between tremolite and actinolite, most often tremolite.
Okay, so it's a metamorphic overprint of some kind of the original.
They are all metamorphic rocks. So we print the typical petrographic names of the magmatic stones, but most of them need a prefix meta gabbro, meta diabase, and so on.
Good, got it. Thank you.
Marcus, could you share with us the web address of the spreadsheet that you show during your presentation?
Yes, I can send you. It's no problem. I sent by email, but it's all in German. So I've never presented this internationally. So if you are familiar with German, it's easier. It's a simple calculation tool, so I can give you the address and you can try something, and if you're interested, just contact me.
Okay, I'm very interested in the compositional ranges that you selected, because we have tried to do that maybe on a more limited number of samples recently again to adopt an automatic method of selecting what is asbestos and what is not. So we use a PCA to discriminate among asbestos minerals, and so it's very interesting for us to double check what we did with other compositional ranges. The one that, so I don't need to go through the German. I just need to see the number of your compositional analysis, your compositional ranges.
Yeah, this is part of the table. So all the data used for discrimination and distinction are part of the table. What I said, what you see is just the part of the screen of the whole table. for the input and output of information, input of analytical data and output of hits. And if you scroll in this table, you find all the columns with the chemical composition of the different minerals, of the asbestos, and also of the element ratios that are relevant for this distinction.
Okay, fine. And besides that, Ariel is asking for the document, even if it's in German, so she can read that.
Yes, okay.
Thank you. Okay. So I don't know, for some reason all the people from Australia are leaving the room. I don't know where they have to go. Anyway, so I think we skipped the question time for Bradley as well. So is anyone want to know a little bit about the Calaveras Dam? Maybe now, Mark, you have time to answer the question that it was posed about the analytical tool that you use to discriminate the calcium amphiboles. Mark, we don't hear you. No? No? Something wrong with the microphone. Yeah, just put up signs. No, it's not. It looks like is your microphone connected? Do you have any headphones or anything like that? Okay. Bradley, maybe do you want to say something more about the analytical method if you except that you use EDX?
No, not really, other than that, yeah, Mark did research and develop a boundary between amphiboles based on the EDX spectra heights, but I hope I don't misstate anything, Mark, but it's somewhat qualitative. It hasn't been, haven't been checked with standards and so on, but it did a very good job for us, really. It did separate everything into species, and at the subspecies level, like iron glaucophane versus glaucophane, no, the technique really can't distinguish those really well. I think it did a really good job at the species level, glaucophane versus riboside, for example, but there might be, a boundary issue, near the boundary. But you'll see that most of my analysis, I used the 4 major subgroups, and there we, definitely have really good data on that. But it would be nice for Mark to talk about what he did to determine those boundaries, because it is pretty important. One thing I will say about it is that this is a system that Mark developed for this project, really, and if we ever wanted to use this across laboratories, we would need to develop a particular system that's standardized so everybody gets the same answer.
Good. I don't know, Mark, is your microphone connected now? Let's try to. Is there anybody that can read lips, maybe?
Come on, Mark, Robin is waiting for the answer.
I actually had the question was more about like the calcium index, like you had that percentage number. So I wasn't sure if it was the measure of the calcium in the fibers or just a measure of the population of calcium fibers that were there.
Oh gosh, all right. We went way off course on that.
Okay.
It's actually, and I use concentration. Sometimes I use fibers, but everything was normalized by concentration, and it was the percentage of the concentration of the calcic amphiboles with respect to all of them.
Perfect. Thank you.
Boy, we could have solved that in 2 seconds.
I know. Well, I'm still interested in what Mark has to say. So if Mark gets back on here, because that's what I'm actually working on an EDS technique to try to standardize lab EDS data. So we're all calling it the same thing. But the IMA messed up my classification system when they went to the 2012 because we can't measure iron 3. So working on it.
Okay, Mark, I remember you. So please get a microphone. Okay, so what about the young people of the group? Maybe you want to ask something. Dad, I see you're still online. Gaia, Jasmine, don't be shy. Huh?
Hello, everybody. My name is Eric Bruckner. I'm with the North Coast Air District. Everybody hear me?
Yes, Eric.
How's everybody doing? First of all, I want to say thank you for everybody taking this whole project on, all the coordinators, TEM labs here in California, and the international labs. Outstanding, neat forum. I got a question for Bradley.
Yeah.
You know, from the enforcement, I'm an inspector here in the North Coast Air District, and as we look at our application of CARB 435 and enforcing the ATCMs, as we've seen in the past, it gets, as we look into speciation of fibers, qualification and quantification for on the boots on the ground, interfacing where we get triggers, and then speciation now, looking forward, how is an enforcement application to these sciences coming together? I think Nash is doing a good job looking at coordinating and getting everything on the same page. What do you see going forward as an approach for trigger enforcement applications of these sciences? Thank you.
Enforcement in terms of maybe the all amphable metric, things like that?
For triggers, when we get into in the ATCMs, if there's a trigger found on a property of 0.25, yeah. I'm talking about going forward for use in a facility or you know, roadways, so forth, as we then go into finding more specifics in these sciences, coming out with speciation. Then we got qualitative for fiber size, and then we got quantitative. So it's typically the quantitative that we look forward when we get blending of the speciations with qualitative. What are we looking at for triggers? Looking forward, what do you think? Makes sense.
I'm not sure what you mean by triggers. Triggers meaning like a threshold of some kind?
Threshold. Yeah, exactly. Okay. For an enforcer. I'm sorry, sir.
Yeah, I'll just give you my opinion on that whole thing. I mean, we're stuck in the NOA world. We're stuck with the regulations that came out of building materials. It's very, very, very problematic in two ways. One is for example, in building materials, the 1% is not a bad threshold because you're looking for, at least way back, was asbestos applied and was it not applied? If it wasn't applied, it'd be below 1. If it was applied, it'd probably be above 1. Okay, that's great. Doesn't work in NOA. You know, it's a sliding scale. And also the speciation doesn't work as well because, as you know, there's the 5 regulated amphibles. But even within the regulated amphibles, there are some laboratories, for example, with Rebecite, will exclude that from reporting if there's, you know, any amount of aluminum, right, that is found. Boom, not asbestos, when in fact, you know, the health risk is the same. And so then of course, like in our case, we have this fibrous glaucophane, which is very, as far as I'm concerned, pretty much the same as crucidolite, you know, Rebecite. Yeah. So it's really problematic, in the NOA world. I look at data, and see, well, what are the amphibles that you found in your air samples? Well, if it says none detect, that doesn't tell you much at all. That just tells you that this very, very narrow slice of compositions within those 5 amphibles are not there. So I see a need for several things. Okay, first of all, you could eliminate that problem by regulating all amphibles, right? And if you do that, it doesn't matter if one lab got glaucophane, another lab got Rebecite, because you're going to throw them into the same pool, right? So you're capturing everything. I'll give you an example of how important that is. I don't think there's anybody who's going to say that the glaucophane, the fibrous glaucophane, the blue schist, does not pose a health risk. But on that project, if it was given to just a normal commercial laboratory that eliminates amphibles based on aluminum content or what have you, we would find that the reportable amphibles would have been less than 1% of all the amphibles found on the site, right? We would have way under, and not only that, they would have been eliminated during the investigation process. So you would have a none detect on the blue schist, And therefore, we would not have needed the dust control measures. We would, or at least not how to apply them, respiratory protection for the workers. We routinely had exposures above the PEL, and an air monitoring program would not be needed at all, when in fact, that's not true. So there's that. And there's also the weight percent. You know, we've had some discussion about that, how it's not a good indication of how much asbestos is there, right? You can do a simple calculation of length versus, you know, width, get the volume, specific gravity, and you get weight percent. And what you find is the thicker the fiber is, the higher the weight percent. And what you find is the samples, especially in alluvium, the weight percent is dominated by sometimes one big, long, thick structure, right? But if you convert that to, you have to use TEM for this, fibers per gram, now you've got some kind of an index that tells you something much more interesting as far as the potential for exposure. You'll also find that there's this arguments about cleavage fragments versus asbestiform. You know, should you include them? Well, fibers per gram will help solve that a little bit, because what happens if you have cleavage fragments in your population, because they're wide, you get high weight percents. So you can have chrysotile in a sample with huge numbers of fibers and a very low weight percent. But you can have a few cleavage fragments with a very high weight percent. But because cleavage fragments, you know, tend on a population as a whole, fewer countable structures by far than asbestiform, then you're going to find that the fibers per gram contributed by cleavage fragments is far less than the fibers per gram by any asbestiform population. And therefore, they become somewhat subordinate simply because there's fewer of them in your population.
That's outstanding. So when you look at the representation, general representation of a sample for a property, I mean, that's getting into another issue as well. What are your thoughts on that? Getting a true representative sample of a site.
Oh my gosh, that is $1 million.
That's a big one. Sorry.
No, you know, and I've had some discussions just recently with this group and Mark and Sarah also more specifically about in this group that we have here, we're interested in writing some kind of guidance on how to do sampling. Right? The best guidance we have is the California Bulletin. I can never remember it. What is it? 524?
Special publication 124.
124. And yeah, it's really good. It talks about a lot of things, but what it does not really go into is what test methods do you use? How do you sample? You sample a hard rock differently than you sample alluvium. How many samples do you take? You know, I advocate for incremental sampling, right? You know, you take a sample, there's going to be a lot of judgment. A geologist, there's always going to be judgment by a geologist, and that is why the geologist has to know what they're doing with respect to NOA. And you have to just make a decision, and it cannot be, in my view, it cannot be a cookbook, right? That used from every project. You know, every project I go on, I have to stop and think, what am I looking at? What are my goals? How am I going to sample this? And I include that in the report. So with alluvium, you need to do incremental sampling, but you also need to do targeted sampling as well. And remember, OSHA does not allow compositing of samples.
Right.
So how do you resolve that? You know, when one single sample in an alluvial deposit could be very high or very low, you know? So in other words, it's hard to answer that question. I think it's a case by case basis. Geologists have to understand the big picture, know what they're looking for, and sample appropriately. But you need as many samples as you can get. And the incremental sampling for me is the only way to average out those little chunks of, you know, actinolite that you might have caught and get ground up versus the ones where you don't, you know?
Exactly.
In the end, it's going to be just like any other geologic investigation, an opinion, but that opinion has to be based on experience by the geologist and an understanding of all the issues.
Thank you very much, Riley.
We do need to get some better, no, I shouldn't say better guidance, some augmented guidance to the special publication that goes more in detail about all these techniques and the pros and the cons and things like that.
Very good. Thank you. I look forward to your future work, Drew.
Yeah, this is Mark. Can you hear me now?
I think Mark is back with his microphone, but we had also contribution for Marcus. I don't know if it was on this topic, Marcus. You raised your hand before?
Yes, it was concerning what something Bradley told. We had a lot of experience with these with the detection of mass of asbestos particles. And as he told, you find some blocks of asbestos particles, very thick and short particles, and they have a big mass, and very high number of very thin particles giving you low mass. So therefore, the mass content is not of that importance. So in the legal regulations, we have this formal aspect of 0.1% as the limitation, but the determination of asbestos content typically is not because we want to look how much asbestos is in it, but to find if there's asbestos in any way. And the next step is not to determine the exact amount of asbestos in the material, but to detect the exposure. So this is the ranking we do in our regulations. And one of the problems determining the asbestos amount is it's not very suitable to just take 2 or 3 samples of a quarry, take five pieces of block and grind them and look for asbestos. So what we do is taking dust samples during crushing. This means we get a representative portion of the samples in the kind of dust representing, for example, 50 tons of material. We take the sample 4, 5, 6 hours a day, and then have, let's say, 100 or 200 milligram dust on the filter of inhalable dust. Take an aliquot of it, and we can determine the particles released by this process, representing the material and the crushing process. So we have a representative sample for a big amount of material from one quarry. And this is something that works very, very fine. And therefore, I also told you there is an obligation always to print the number of particles per milligram, or as you told, particles per gram. This really helps you to get an impression about the potential of fiber release from this material. It's totally different if you have, let's say, 1% asbestos by releasing 50 fibers per milligram or 20,000 fibers per milligram. And these are the interesting facts, just with a focus on the exposure of the people working there.
I can't agree more that the air samples, activity-based sampling, if that's the way you want to look, call it, is the bridge between what you see in the ground and what you might see on a personal sample or on a perimeter sample. It's the link between the two. The problem we have is that all of our regulations are based on bulk sampling and the 1% or 0.25%. So therefore, we must do a geologic investigation. We must report them by, whatever it is that PLM, surface area percent or whatever it is that it reports, or weight percent by TEM. We're bound by that. And I've had some experiences with some of our local regulators, DTSC, for example, that regulates in schools. And there was one school site where there was chrysotile and amphiboles, and the concentrations were extremely, extremely low. And it was one case where I argued that we really don't need to have a response action, air monitoring, capping, and all that. The problem was there were a couple of large structures of cleavage fragments that brought it above their 0.01 threshold, which is, a low threshold. It doesn't take much more than a single cleavage fragment to get above that, and convert it to fibers per gram, like I did, and showed them, that we really have a low amount of asbestos. In fact, I compared it to the blue schist fiber per gram, actinolite fibers per gram, hornblende fibers per gram, and showed them that this is a really low risk site. But the regulators, basically, they said, we understand all of this, and you're right. However, we have our threshold that we must use. There we go, hundreds of $1,000s project on a school site because of that. So we're really constrained by what we are required to do by regulation, and it's going to require, EPA, OSHA, whoever, to somehow drift away from the building material metrics and develop something that's new and makes sense for naturally occurring asbestos.
Yes, take influence on the regulation. I tried with success because this is a fact, as you just told, and I tried some years to bring this influence to the regulators, and it worked. So now we move from the mass content primary to the exposure, but we have the same problem now with waste. So all waste control is also regulated by mass contents, and they still didn't understand this. So we have the same problem what we solved for the exposure of workers. The same problem now appears for the waste management, because European regulations also always look for 1 fiber or 1% or 0.1%, and it's the same difficulty.
Well, Sarah, you mentioned that new talc method, all right? Yeah, you're there. And in that new talc method, they did mention recommendation, I think they said consider, but to use something like, they mentioned that mass percent is highly problematic, and moving to a fibers per gram type metric may be the way they would want to do that. I'm hoping that that's what they do, because that would then open the door for more and more look, investigation, comparative analysis, whatever. And then we'd be able to go to a site and say, based on fibers per gram, there is an indication that there is a low, medium, or high potential for exposure, and move forward based on that.
Bradley, can you hear me now?
Mark, you have a
Now you have feedback.
Mark, you have a very strong feedback from the microphone. Is there any way that you can keep your microphone more distant from your speakers?
Or try turning down your speakers when you talk.
Yeah, exactly.
Feedback.
Turn down. Yeah, about the fact that we are going to have these changes maybe in regulation. What is striking me is that if we move to a weight percent, like 0.1% that we use now, the 1000 ppm that EU regulation is asking for the waste and for classification of spoils. If we move to number of fibers per milligram, we have to take into account that what we analyze is actually an artifact, something that has been manipulated in the lab or even before. So the actual number of fibers is very dependent on on how we process that sample. So it's not like that we can just rely on that number as if that number is the real hazard of that material, because if you grind that materials with some tools or for a longer time, then you will get more fibers. So we have to take that into account.
Yep. Any method has to be standardized, and then you use that result accordingly, as long as everybody is doing exactly the same thing.
Yeah, but Bradley, that when you have like a natural rock in your hand, just the rock can be so different one from each other that the very same milling time and milling procedure can give you like very different results. So I don't know. I still think that the weight percent can be something closer to what you get from infrared spectroscopy or XRPD. If you move to that, I mean, in Europe, we have SEM method to measure asbestos quantitatively as a weight percent amount. So there's a lot of concern about those methods, but nonetheless, they are available and they have a very strong assumption. Every fiber is just a cylinder, but at least you come to a number that is less dependent on how you manipulate the sample before.
Can you hear me now?
Yes.
Much better.
Amazing.
Mark, wonderful. Mark, you can speak for at least 20 minutes now.
Okay, yeah. Okay, now I have the podium here. So, Marcus, I thought it was very interesting what you presented. You were talking about the dust that you were sampling next to the piles or the aggregate crushing operations or things like that. I was wondering whether you had done studies where you took the actual rock and crushed it and then compared it to what you saw in the dust. That's one thing. The other thing is, we've seen that the proximity to the source of the dust has a huge effect on the number and the size of the amphiboles. That very quickly the large amphiboles drop out if you're, as much as 20, 30 feet away compared to being right close to the source.
Yes, what I showed you in the regulation tries to come near to practice. So the primary aim is when you have material that is used in praxis to get the dust which is produced in practice, and don't do something in the laboratory if not needed. So if you use any kind of material that is used in a mechanical processing, then we take the dust from this processing because this is near to the exposure. And there's another method, I don't present it here, is, for example, if we have a material that is not produced in Germany, it's an imported material from Sweden or from Austria, anywhere, and we don't have information about the asbestos content, then we take the worst case, take the material and grind it totally. And then all the things happen that Francesco just told us. Not we, but another laboratory tried to optimize the grinding process, and it's easy to do. You take one of material containing amphiboles, and you grind it 2 minutes, 10 minutes, 20 minutes, 30 minutes, and you see there's a maximum. 2 minutes you have less, 10 minutes it's more, and the longer you grind down all the fibers that appeared in between. So grinding process is always a random. Because even if you take the mill, take 20 balls, take it in a box like with this size, you always have things that influence the grinding process. You will not be able to reproduce a grinding process because it depends on the size of the balls. It depends, for example, on the frequency of grinding. If you add water or not, how many material you put in the box of grinding, and how many balls in which relation they are. So it will never be really represented and reproducible. So the aim for us is use dusts that are done in technical processes. They always represent what happens at the workplace, and only if nothing else is there, take the material and grind it. And we know that there are differences. But as I told you, the analysis concerning mass is always most often done just to look if there is asbestos, and if you find something, the main task is to determine the exposure. So the mass determination is just there to see if we are in the scope of these regulations or not. So we divide the different quarries we have by doing this process to see if we do 3 times a measurement at the crusher. And if you 3 times won't find any asbestos fiber, the quarry is away from these regulations. Because in former times, we tried to find out if there's asbestos by just doing exposure measurements. And when you stand with the wind, you will never find an asbestos fiber. So therefore, it's just also to get clear results. So this determination of mass is just a link to see if there's a quarry concerning asbestos or not. Because we have a lot of a lot of quarries that some of them contain asbestos, some not, and you won't see on the stone itself.
Okay.
Okay, thank you, Mark. Well, it's dinner time here, and most of all, I finished my beer. So I don't know if there's anyone else that wants. I mean, I can even leave the WebEx room open, and we are just recording all this chat. And maybe you Americans can keep talking until it's the night. I
We
don't
can
know.
have here.
Just tell me how long you want. I mean, I'm seeing people here behind my back that got my screen. They are getting ready for dinner. So,
if it's possible, I also have to leave in some minutes, but I would have one question for Stephen Miller's presentation. That was very interesting. If he's still available.
I think he just left.
He just left.
I'm still here, Marcus, for the moment.
Yes, something what was very interesting that you told that you would like that you are going to use samplers, cyclone samplers, to separate the different fractions of fibers, and you wanted to sample the respirable fibers with a respirable sampler. So this seems to be consequent, but in the end, if you look for the dimension of respirable fibers, they are not in all respirable dust, because when you take a particle with the size of, with a thick of 2.5 micron and 20 microns length, it has an aerodynamic diameter of, let's say, 20 or 30 micrometers. So when you take a cyclone for respirable sampling, a relevant portion of the respirable samples will not be placed, will not be caught by the sampler. I remember this project on thoracic sampling, because thoracic sampling, I think, represents the respirable fibers more or better than if you do it by respirable sampling.
Yeah, so we'll be looking at several different types of samplers, but the real question is, does the way we're currently sampling, which is essentially a total particulate sample, right? It collects everything. Is that really is that representative of what we're breathing? And there's not been a lot of work that's been done in that particular area. So NIOSH, we would like to sort of look at that and see. I agree that if we use a respirable type sampler or some sort of fibers may be excluded, but if that's the case, then maybe they're also excluded as in our inhalation pathway. So I think that's type of information that needs to be a little more clear.
Yes, but I think you get in conflict with the WHO definition. So when we on one hand say we want a respirable fibers concerning our respiratory system, this is the one theory. The other one is we have these WHO dimensions that are critical in my mind. And I know the project of EPA reducing, talking about different fiber dimensions as a select item, let's say the dimension of less than 0.4 micrometer thickness. And so this would be very leading for this. But up to now, we have as a convention, this WHO convention. This includes also thoracic fibers. And just when we talk about NOA particles, it's really relevant. We won't have this discussion if you only look for asbestos coming from typical products by procedures. But if you look on anything that comes out of quarries, we just most often have to do with particles that are not typical respirable but thoracic particles.
Yeah, and so, hopefully we'll be able to look at all of that information and see exactly how these samplers are measuring the particles that we're breathing or that are being emitted into the air. That's the idea.
Okay, thank you.
Okay, wonderful. It's a great discussion. I don't know, Sean, do you want to say something? I don't know. I saw you opening the microphone.
Sean, did you want to say something? You're on mute.
Yes, I couldn't remember, red mute or red not mute. Okay, Steve. Okay. Steve, didn't you talk about water elutriation, and haven't there been a few good studies showing correlation of water elutriation and separation of fibers from source material?
We did talk about, or we've looked at water elutriation, and a lot of people are into the heavy water type thing too. My impression is that the research that was done using water elutriation water elutriation in general is not going to exclude the very, very small particles. And I think in some of that research, those small particles actually may not have been counted, so they were saying it did a nice job separating, but they didn't really look for particles smaller than 5 microns. And so a lot of these smaller particles just weren't counted in some of the literature. That's my thought.
That's true, but it still has usefulness for correlation for what could potentially get in the lung. And then if we measure everything and then go back to the data set and say, well, we know that this isn't getting to the alveolar region, at least we have the data.
Exactly. Well, I mean, yeah, and I certainly see that. So the research we're doing isn't to try to exclude anything from the measurement. It's simply, what do we think is the real exposure to? Well, I mean, we're working with our mining stakeholders, but that would be the idea. What is the real exposure? And there's not really a whole bunch of work that looks at that. So I thought it would be an interesting pathway to try to unwind.
And also thank you for a very nice presentation.
Okay, very well. Mark, are you ready?
So why don't we just sort of wrap it up here, and then we'll see everybody tomorrow morning.
Yeah, I just wanted to thank everybody because it's been like a great day with more than 100 participants at a certain time. So I'm very happy. I didn't thought it could be so good, and so once again I just have to want to thank you all about this great presentation, all the speakers and all the audience. We still have 38 people resisting at this time. I assume they are all from Americas, but who knows? Yeah, I see some people that want to have dinner now. Jan and Jasmine are shaking their heads. So thank you, everybody. I'll see you tomorrow, 5 p.m. Central European Time. And it's been a very good night.
Thank you, all you speakers. Thank you.
Thank you.
Auf Wiedersehen.
Auf Wiedersehen.
Good Nacht.
Bonne soirée.
Ja, gute Nacht. Ja.